All right, so to solve for this, I need some variables on this, and I don't know if I have them handy. Let me just see. I thought I did, but do you guys know the variables on this? Did you see this before? Let me see. I might have it here. It's not here. Ah, up here. There we go. I got some variables. Okay. So I'm going to say that this picture, A is 50 millimeters. I'm going to say C is 1400 millimeters. And E is 30 millimeters. I want to then find out what D is right there. Okay. We want to find out what D is. So first thing I do on this is I know that this measurement right in here is 50. So I'm going to draw myself a little right angle triangle right in there. See, here's the right angle. Anytime I have this would be classified right in here. This is going to be classified as a travel. And if I want the rise or the run of that travel, I take 50, and that is my travel. I'm going to divide by 1.414. Oh, there's another measurement that I forgot. R is 150. R is. So this turns out to be 35.36. Yes? So this line right here is 35.36. So now I have that, and I know that R is 150, so I could draw another right angle triangle starting right there. And I'm going to bring it all the way to the top and follow it there. There's the right angle. And now I know that this is 150 in here, and this is 35.36. So this line, a run of this line is equal to 185.36. That line right there is 185.36. And to get the travel of that, we have to multiply by 1.414. And I can get the travel
262.1.
That is correct. So that is 262.09 or 262.1, close enough for me, right? So that's 262.1. So that's this line right in this location here, gentlemen. And so now that that is 262.01, I'm going to just write that in a black pen. So this line right here, we determined to be 262.01. Well, now that I know what that is, here is another right angle triangle. As you can see, if this is 262.01, this is 262.01, isn't it? The rise and the run are always the same on a right angle triangle, 45-degree right angle triangle. So that gives me what H is. H has to be 262.01. It's not quite D yet. But look, I have the measurement here of E being 30. So that means this is 30 and this also has to be 30 because we have another right angle triangle right there. So 262.01 plus 30 is J. So J is 292.01. And now to get D, I simply take 1400 and minus off 292.01. And that's D. How's that?
So just remember 1.414 pretty much for these. And you're going to either divide or times most of the time.
That's right. Find your right angle triangle. Find what your rise and run is and know what your travel is. You should be able to figure that out. And I did it in different colors so you could see those triangles. Right? That's where triangles come. Hi, Kat. All right. So listen, guys, again, I want you to bring questions. I don't want to just teach lessons to you. You are supposed to bring questions that you have for me.
We don't have math class.
Okay,
You-
I got a good one for you to go over.
Okay, sounds good.
Do you remember that Red Seal quiz that Fred sent over to you? That backside and foresight. You want to go over that? That will probably help out everyone in the group.
Okay, sure thing. Thanks, Jared. I think I have something here. Let me just pop that in.
Here too, you do a little fixture spacing example. I can't remember that one very well. Hanger spacing.
Okay, so now we have this backside foresight kind of deal, right? So we all know what an invert is, right? We do know what that is. Invert is the bottom of the inside of the pipe, correct? Yes. Okay, so we have a foresight and it says here 1.82, but inside the manhole here, I don't know, that they're coming up with new terminology for that because, you know, it's not, I don't know, the vernacular is not correct anymore. I mean, I don't want to call it a woman hole. I mean, that's still not correct. And I don't think a person hole is correct either. I'm not sure what they're calling these anymore.
A service hole?
Personnel
Yeah.
access or something like that.
An access.
Service hole isn't better either, Daryl.
No, nothing's better. So I digress. Sorry, that was just a little joke. Okay, so there's the measurement. We're going to go all the way down to the invert, right? So that's really 1.82, and we have to add 1.02 to it, right? So we get 2.84 meters deep right there. Is that correct? You guys concur with that measurement?
C.
C. Okay, so now we have a backside over here, but we have a pipe that's grading downwards this way, the direction of flow, and it gives us 25 meters at 1%. So I have to find my grade. Really, that's important to find the grade first. So to find grade, you all should know this formula triangle where the drop is equal to the grade times the run. Don't ever forget that for sure. Okay, so we take our run 25 meters and multiply it by 1%. And of course, that becomes 0.01, right? And that comes out to how much?
0.25.
0.25 meters, correct? So we have 0.25 meters as our grade. So over here to the 0.64, so that's 0.64. We're going to add our 0.25 meters for the grade that comes up, right? So we're going to add that. So that's going to be 0.89 meters over there. And now this is how simple this is. 2.84 minus 0.89. And that comes what? 1.95 is X. How's that? Got it down?
Yep.
All right. Now I could see if I could pull up a fixture spacing something.
Is it the same as hanger spacing?
Well, you have to count your spaces. That is very correct.
Pretty much it.
Space counting is important.
There's a
I don't
good,
know.
there's a good red seal practice one. Give them 6 labs, dual vented, and the question is, what's the distance between the vents?
Oh,
Yeah, that's a stupid question. We went over that a week
Good
or so
question.
ago, Doug.
that's right,
We
Jared.
went
Yeah,
way too far with it.
we did go too far. So, and we didn't count it correctly. And the only thing I don't have is any of the parameters around that particular one.
I
So
have
we
the
have-
question. Do you want me to share my screen?
Sure, please do. I'll snip it and then I'll throw it on my screen. Yeah, you bet. I'll stop sharing there for a second. Go ahead.
Yeah, I'm just pulling it up. 1 second. Come on, Fred. Where'd you put this stupid thing? Sorry about this.
Thanks, Kat.
I don't even know how to leave this damn thing. Jeez. Where's
Yeah,
the
we get
leave button?
used
Oh, there
to
it
what
is.
we use. Yeah.
Yeah, okay, I got it.
Okay.
All right, have a good one.
Take care. Jared, you're leaving us hanging here.
Yeah, I'll let you know when I find it. I'm scrolling through Fred's exam right now.
Okay. Geez, I guess I should get that exam.
I thought you had it.
I don't have the exam. No. Listen, I may have the exam, but I don't know where I put it either.
What have you been told,
Oh,
Doug,
here it
by
is.
people that have done this DSA, done the interprovincial? Like, what have they came up with for questions, for math questions,
Rolling offsets.
rolling offsets?
Oh, there it is, Jared. Okay, let me just write some of this stuff down. Hang on a second here. So that says 6 labs spaced equally, 530 centimeters long wall. And it's with dual vents. And we need to determine center to center of the vents. And each fixture is 51 centimeters wide. Okay, thank you. Okay, so there's the parameters. Let's see if we can at least draw something out relatively square. Not going to make any promises. Woo, that was good. Okay, so we have 1, 2, 3, 4, 5, 6 labs. They're not equally spaced, but pretend they are. All right. So each lab is 51 centimeters. The entire wall space is 530 centimeters. So our dual vents, we're going to have a vent right here. We're going to have a vent right here. And we're going to have a vent right here. Yeah. Maybe I'll move this sink over just a little bit more. Okay. So there's 1 dual vent, 2 dual vents, 3. Okay, that's 6, right? Does everybody agree with that statement right there? Yeah.
Yep.
Okay, so we have to count the spaces between. So we have 6 labs, and if we divide the 6 by 570, so 530 divided by 6. Is that how we got that to start?
Doug?
Yeah.
I think you're gonna take it way too far again, buddy.
Yeah,
So you
you're right.
take since you have 6 lavs and they're all dual vented, you get 3 vents total. So you take your 530 centimeters and divide it by 3. That gives you your answer. End of question.
Oh, wow. See how easy that is?
Yeah, that's why I was saying we were taking it way too far because we were looking at it and doing each fixture spacing, trying to get the exact number in between the two
Right.
sinks. That's taking it too far. You just divide the total by 3.
So that comes out to 176.66 centimeters.
Whack.
Super whack.
So there, and there.
So if you do it the long way, you get the wrong answer.
No, it just it's a rabbit hole because then you're counting the spaces, the lab, the space, and the lab. Yeah, that's what we did last time, eh, Jared? We went far.
Yeah, we ended up counting a space and then half a space plus like a quarter of a space, and we ended up with way too big of a number.
Yeah, we did.
At the end of the day, I think we all just gave up on it.
Yeah, we did.
Well, that's hopeful.
I can't remember how to do rolling offsets very well. That'd be pretty awesome to go over a couple of those if you got any.
Sure.
Is
Now
there gonna
there's
be a trench spacing?
2 formulas you have to remember when doing rolling offsets. Let's put in this one. And let's put in another one. Let me just.
Is your
That's what
computer
you're using.
touchscreen?
No. I have, I gotta show you what I have, I guess.
Yeah, please do.
Why, do you like this program?
Yeah, and you should really teach John how it works.
Okay, do you see my video here? You see my
Yeah.
little pen?
Yeah.
I am just using a tablet and I'm drawing on the tablet.
Yeah, okay, how do you have it like set up? Cause I literally have a tablet and I've got a pen in the other room.
Well, mine just plugs in and I just have this wireless pen and I'm allowed to insert documents. I'm allowed to insert PDFs. I'm allowed to insert PowerPoints, pictures, whatever I want. I can insert onto this and then I could draw all over it.
Wild.
Yeah, it's pretty cool, eh? And
Yeah.
then, you know, this is what we did already. If I expand out, look at this. It's all there.
Yeah.
And I can email this out. I can add people to the screen if they have the same kind of whiteboard and they could participate in the whiteboard with me.
You didn't have to download like a program on your app, on your tablet or anything?
Well, I had to download the drivers for this particular tablet. And the reason I like this tablet is because it was only $60. Right?
Fuck.
I'm poor. You know that. We're all poor. We're instructors.
Yeah, teachers don't make anything, right? It's only
No.
after the 20 years.
Yeah, and I haven't been there 20 years yet. If I hit 20 years, I'm going to retire. Let's put it that way. Okay, 2 formulas required for rolling offsets. Okay, everybody, 2 formulas. If you're working with 45s, on a rolling offset, this is the formula take to find the travel. You're going to take the rise squared and add the roll squared, square root it, and times it by 1.414, and that equals the travel on 45s. Okay, if you're using 45s on your rolling offset. If you're not using 45s, if you can see this one over here that I have here, it says 51 degrees. If you're not using rolling offsets, you take the roll squared plus the rise squared plus the run squared, square root it, and that equals your travel. So those are the only two formulas you need to solve for rolling offsets. For example, this one right here with the 51-degree angle, we simply take 11 squared plus 10 squared plus 12 squared, square root it, and that equals your travel. Now, you should be able to know that you have to use this kind of, well, you don't have to use this calculator, but this is the one you get, right? I know you guys know this. I've seen you guys before. So if I go 11 squared plus 10 squared plus 12 squared equals 365, shift square root. This roll then, or this piece of pipe right here, let me even use a different pen color. This pipe right here, right there, is 19.1.
Easy.
Inches.
Easy, easy, easy. Now, this one over here, it doesn't actually tell me what my angle is. But we can kind of prove it in a way if the math works out. Because the roll squared plus the rise squared is actually, with a square root, is actually equal to the offset or the run or the set. So we could do that 8 squared plus 6 squared, shift square root. So if I go 8 squared plus 6 squared equals shift square root. So this equals to 10. And then I take that and times it by 1.414. And my travel here is equal to 14.14. Now they will give you two variables. Use this. They give you three variables. Use this one. Okay, there you go. One or the other. Now, they're going to put extra legs on some of your rolling offsets, right? They're going to put an extra leg down here and they're going to say, what is the distance over here or over here? They're going to do some weird stuff. But remember, none of this is to scale. It's an optical illusion. It's not to scale. None of the pictures they use on these exams are to scale. So some of the numbers, it doesn't look like it'll fit, but it does. And you got to remember, if you're using 45s, then the run is equal to the rise.
Hey, Doug, do you know if the IP gives you any like formulas, like triangle formulas, or do we need to know that stuff on IP?
Well, I think you get the same formula triangle sheet that you do for a TQ.
Oh, okay, sweet.
Is there anybody in here that's not a fourth year that they need something looked at?
Yeah, there's a couple peasant second years.
Okay, well, listen, let's answer your questions first. Philip, why don't we ask you ask your question, because it might be good review for these fourth year guys too. So shoot.
It was a simple down version of what you just did then.
What, offsets? You're talking about
yeah.
offsets?
Yeah.
Equal spread offset or a round the corner offset or what? Do you have a picture of it? Philip, we lost you.
do have a picture of it.
Okay, I'll stop sharing. If you want to share the picture for me, see if I can grab one from somewhere. Okay, one of those. Okay, gotcha. I got it. Okay, so that's a simple offset around a corner. Let me just pull one of those up.
Yeah, that's it right there.
I got you covered, man. Okay, so here we go. We want this dimension, this pipe dimension down here. So anytime you do not have a measurement from the corner, and in this case, we do not, we have to start from the center of the object that's there. We're going to draw a line parallel to the outside wall. This is not going to be pretty, trust me there. And a line parallel to that outside wall, touching the pipe, and we make a big triangle. Woo! And now we cut that down the middle because this is two right angle 45-degree triangles. And in this scenario, we know that the rise and the run are always the same in a right angle 45-degree triangle. So this line right here, let me just use a different color. This line is 18 and this is 16. So this total line is 34. And if the rise is 34, then the run is 34. And that's 34 on each side. So this measurement right in here is equal to 68. I just have to now solve for this piece right in here. And I'll do that by drawing a small right angle triangle, 45-degree right angle triangle right in this location. And now I need to get the measurement from the line to the wall. I need this measurement. And I take 18 and I add 15. So this line or this measurement is 33. And if I minus off 12 that's sitting over there, minus 12, that gives me 21. So this line right here, this line is 21. So for me to get the travel, I will take 21 and times it by 1.414.
29.694.
And then that number, yeah, 29.964.
694.
Oh, okay.
And do the same for the other side and then add that together.
That's right. So here is the travel that I need to solve for on the bottom part. I'm going to draw a right angle triangle right in there. And I take the measurement from the orange line to the wall, which is 18 plus 11. So this is 29. And if I minus off 14 from the bottom, that makes this line 15. So then I go 15 times 1.414. And that will give me that measurement there.
21.21.
21. So this is 21.21. And I simply add them all together. 21.21 plus 68 plus 34 gives me this dimension.
Thank you.
You're welcome. Now, second years, do you have another question there? Before I go back to these guys.
Not yet.
Not yet. Okay, thank you. Okay. Fourth years. Should we do a little volume and capacity with you? Hemispherical tank.
Oh,
You know how to,
buoyancy.
pardon me, Mike?
Said buoyancy at some point too. Shit, I could do all of them again.
Do you want to?
Just hit me, Doug. Whatever you got.
You want to do some? I could do a quick buoyancy with you. Quick.
Are we going to see that on the IP? I remember how awful buoyancy was.
Well, buoyancy is not awful, and I don't know is the question.
A hemispherical tank would be good to do once too, for sure.
So let's do that first. I will get an image here if I find one somewhere. Clearly don't have one handy. Hang on, I do, but I just gotta mine it out here. There you go. Okay, let's make that a little, get it off of that one. Okay, so we have this document. It's a little big right now. Let me just shrink this down. There we go. Now I can zoom in. Okay, so there we have a hemispherical tank, and I want you to calculate the volume, the surface area. I want to know how many imperial gallons is in it. Okay, so I could ask 3 questions on a hemispherically ended tank. So let's do the volume first. So anytime I do a volume question, I write down my formula. 4/3 pi r cubed plus pi r squared times height is the volume formula for a hemispherically ended tank. Then I write down my variables. I'm going to write down my overall length, which is 15 feet. I'm going to write down my diameter, which is 5 feet, which makes my radius 2.5 feet. And then this gives me the length, or sometimes known as the height of my cylinder, and that is up here. So if my overall length is 15 feet and my diameter is 5 feet, what is my height here? What is that measurement?
10. 10
feet. This is the biggest mistake that everybody makes. And that there is the height of the cylinder. So we really, I'm going to emphasize this a little bit. This height is this height. It is the height of the cylinder is what this is. So now I will calculate the sphere. So 4/3 on my calculator is equal to 1.333 multiplied by pi 3.1416 multiplied by my radius cubed, which is 2.5 cubed. So this is the formula for the sphere. And let me just 0.3333 times 2.5 cubed equals. So that's about 65.45.
Sorry, Doug. Where's the cubed button? Is that shift?
Shift
the
and
plus minus.
It's the play button. It's the triangle on there. It's
yep.
the play button.
Thank you.
Shift X. It's the X3. And now, so that's the sphere. And now we have the cylinder left over, because once we calculate the sphere, we just have the cylinder sitting in here. And that's all we have to do. So that's pi, which is 3.1416 times 2.5 squared times the height, which is 10. And that equals 196.35 cubic feet. And that's the cylinder. And we add those two together to get a total volume of 261.79 cubic feet is my volume. And I could simply then multiply that by 6.24 gallons per cubic foot imperial measure. to get 1,633.6 gallons in that tank.
Hey Doug, would they ever ask you like what would be the water capacity of something like this for propane? Like, or would they
Yeah,
usually
absolutely. Yes, Mike. Yes. I would say that to be true. In any container, they can do that. And we know that this is only, if it's propane, it's only 80% full, right?
42 for water capacity?
42 what?
That's weight, right?
42 what? What is it?
42% by water capacity.
42% by water capacity. So you got to be aware of how to do that too. Okay. So yeah. And then they could say, okay, you have this many gallons. 1 gallon is 109,000 BTUs per gallon. How many BTUs do you have in that tank? Whatever, right? I mean, you can go on and on and on and on these things, right? These containers.
Okay.
And the surface area is just old pi. Here's the surface area formula, right? The overall length times the diameter times pi. And so that the surface area is 15 times 5 times 3.1416, and then it comes out about 235 feet squared. Surface area. They ever ask that?
Cool.
Now, because we're recording this, I will compress it and I'll put it on my YouTube channel, and then you guys can go to YouTube and watch it if you want to review.
Sweet.
Scroll through, do whatever. Okay. Now, do we have any more? I heard some people pop in. Austin, do you need something to ask? Anybody? Any second years or first years or third years that want to ask anything before we carry on?
Would you do the for heating class like the US gallons, BTUs, like heat loss and whatnot for it, or no?
Well, I could quickly explain how to size a circulator.
Yeah, basically.
Okay, so what you do, for example, say I had a house that has a heat loss of 100,000 BTUs per hour, okay? And that heat loss is calculated by taking the square footage of your walls, depending on the construction, et cetera, et cetera. There's a little bit to calculating heat loss in a building, okay? But if I had that 100,000 BTU heat loss, what we do is we take our heat loss and we divide that by how many pounds in a US gallon, 8.33 pounds per gallon. We times that by how many minutes in an hour, and we times that by the delta T of the supply temperature of the boiler and the return temperature of the boiler water. And that is typically about 20 degrees Fahrenheit. Is a standard supply return temperature differential. Now that number can change easily if it's in the question. Now this bottom part comes out to 9,996. So for sizing purposes, we just make that 10,000. Okay. And that is for a standard 20-degree temperature differential on a boiler. Now we just use the 10,000. That's only if it's 20 degrees. And so this comes out to 10 GPM is our flow for our circulator. And that's how you size your pump. that answer your question, Austin?
Yes, thank you.
Okay. Now, speaking of pumps, you guys know if you have a submersible, each impeller is 9 PSI capable of pushing, right? Each impeller in a pump. Now, if you had only atmospheric pressure, if you only had atmospheric pressure to actually lift or suck from, say, a jet pump or a cistern, you would find out how much you can lift by taking atmospheric pressure divided by the pressure per foot. And theoretically, you can only get about 34 feet of suction from any one pipe, and that's in a perfect vacuum. And of course, there is a metric equivalent by 9.81 kPa per meter, and that comes out to about 10.3 meters or somewhere around there. So that's perfect vacuum. The pressure in Calgary is about 12 PSI, so we're already working with less pressure than atmospheric, so we don't have the same amount of lift. And then practically, or practicality, is you're probably only going to get about 25 feet of lift at sea level because of your pipe, your friction loss, your valves, your whatever other things. And so, yeah, so that's how to calculate the lift of any submersible pipe. We know that water has some crazy characteristics, right? We know that water, here, let me just draw an illustration here. We know water is most dense at 4 degrees C or 39 degrees Fahrenheit. We know that the boiling point of water is 100 degrees C or 212 degrees Fahrenheit. We know the freezing point of water is 32 degrees F or 0 degrees C. As water freezes, it expands slightly until it gets to the freezing point, and then it expands 7.5% its volume. And we know that as water is heated from 4 degrees up to the boiling point, it expands again. And it expands about 5% its volume. Hence, we require expansion tanks on our heating systems. And we also require expansion tanks on small commercial buildings on water lines where they have a closed loop or a closed system, so to speak, is where they have a backflow prevention device, a cross control connection of some sort to prevent cross control from the city water from the premise, so a premise isolation. Sometimes you need to put in an expansion tank because of a thermal expansion from the hot water tanks that they're tied to, especially when they're not being used over weekends or nights, that sort of thing. So we have to have an expansion tank installed. And then when water goes from the boiling point to steam, it expands again about 1,700 times its volume. So water expands when you heat it, expands when you cool it, expands when you freeze it. That shit expands all over the place. All right. See, I'm going off on tangents now. Mike, I blame this on you.
Makes sense. Fuck.
Could we do some latent heat calculations?
Sure. I could do one here. So what's really important for you guys at first, before I get to latent heat, is a formula triangle that we use. The heat is equal to the mass times the delta T times specific heat capacity. This is sensible heat. sensible heat is pretty important to us. This is how we calculate how many BTUs it takes to heat something up. This is only heating a substance, whatever it may be. It's not changing the state, right? So the heat is measured in BTUs or kilojoules. The mass is always in pounds or kilograms. The delta T is in degrees Fahrenheit or degrees C, always. So you always have to maintain metric or imperial, right? Once it's in metric, you stay in metric. If it's imperial, you stay imperial. Now, this specific heat capacity is a multiplier. Water is 1 BTU per pound per degree Fahrenheit. And the metric equivalent is 4.2 BTUs per pound per degree Fahrenheit. And that's for water. Then they have ice and steam. And these ones is 0.5 BTUs per pound per degree Fahrenheit. And for metric, it is 2 BTUs per pound per degree Fahrenheit. So those are the ones, those specific heat capacities that we use the most. Now, latent heat is a little bit different. It is the amount of heat required to change the state of something, and the heat is equal to the mass times the latent heat value. So this is a multiplier. And if we're going from ice to water, that's latent heat of fusion solidification. That's 144 BTUs per pound, right? That's ice to water. And then from water to steam, we have, oh, I should do a metric equivalent. The metric equivalent is 335 kilojoules per kilogram. Water to steam is latent heat of vaporization condensation. That is 970 BTUs per pound, or metrically is 2257 kilojoules per kilogram. Mike, I'll answer that question in a second, okay, on the chat. So if I was to do one question on this with this particular formulas here, let me just do one. I will ask one question. We'll do a bunch of calculations, and we'll get to the pressure one that I see there. So why don't I say 3 pounds of ice at minus 40 degrees Fahrenheit to steam at 250 degrees Fahrenheit. How much heat does it take to achieve that? So anytime I do a latent heat calculation or sensible heat calculation in multiple steps, I will draw a line on my page. And this line on my page indicates a temperature scale. And I will put my temperatures in. So I'm going to start off with my temperature of minus 40 degrees F. And then I'm going to write 32 degrees F because I know that is the freezing point. Then I'm going to write 212 degrees F because that is the boiling point. And then I'm going to go to 250 degrees F. So I'm going to start here. I'm going to start with number 1. I'm going to raise the temperature. I got to raise the temperature of this block of ice up to 32. So sensible heat would say take your mass multiplied by the delta T. The delta T is the temperature difference between two numbers. The delta T on this is 72 degrees Fahrenheit. I multiply that by the specific heat capacity of steam to 0.5 BTUs per pound per degree Fahrenheit. And I think, I don't even know what that is. 32 times 72, or 3 times 72 times 0.5. So that's what, 108 BTUs. And now I have this water at the freeze, or this ice at the freezing point. And so I call this number 2. And so at this point, I'll call this number 2. I'm going to melt that ice. So that's latent heat of fusion solidification. And you take your mass and times it by your latent heat value. That should be BTUs per pound. And that is 432 BTUs. And now I have water at the freezing point. So now I want to raise that water up to the boiling point. I'm going to call this number 3, and that's sensible heat. So I take my mass, multiply by my delta T between these 2 points, which is 180 degrees Fahrenheit, multiplied by the specific heat capacity of water. And so that equals 540 BTUs. And now I have water at the boiling point. I am going to add some latent heat to this right here. And I'm going to get it to steam. So I'm going to call that number 4, where we take our mass and we multiply by the latent heat of vaporization condensation. And that equals 2,910 BTUs. And now I have steam at the boiling point. I'm going to raise the temperature of that steam up to 250 degrees. That's sensible heat. Take our mass, times it by the delta T between these 2 points, which is 38 degrees. Multiply by the specific heat capacity of steam, which is 0.5. And that's 57 BTUs. And now I add all of these together to get, let me just add it, 540 plus 432 plus 108. So that is equal to 4,047 BTUs. Okay. Cool.
Hey, Doug, I've got a force question once you're finished here.
Is that the one you put in the chat, Mike?
No, it's not actually. I'll put it in there right now.
Okay.
I have the answer, but I don't understand how it got there. So I will.
Sounds good. Sure.
I need your help.
Okay. Oh, right here, this closed gate valve.
Yeah, so it's a force question, right? And I can't recall force, buoyancy. A lot of that stuff is.
Okay. Well, here, I got you covered. Here we go. Thank you for that. So we know that first off, pressure is calculated by height and density. So P is in PSI or KPA. Pressure is in PSI or KPA. Height is either in feet, inches, or meters, pretty much is all we do, right? So if my height is in inches, I will multiply by 0.0361 PSI per inch. You should know that. My height is in feet. We multiply by 0.433 PSI per foot. My height is in meters. I multiply by 9.81 KPA per meter. Now this is for water. And your question says water. So let me just come down here a little bit. So force or total force is equal to the pressure times the area. So in Mike's question here, we have a pipe with a gate valve on the end. And I want to know the force downwards on this. And force is for the entire area. So we have a 6-inch gate. And I'm going to take that as it is. And we have 46 on this gauge. We have 46 PSI. So we just have to find the area of this gate. So area of a circle is pi r squared. So 3.1416 multiplied by 3 squared, because this is the diameter. That's the diameter. So there it is there. That should be 28.28. I don't know why I know that, but I do. And we take 28.28 and we multiply it by 46. And that's it, Mike. That's all.
Okay, so 6 times 3. Wait, no. 6 times 3 equals, no. Equals 28 times 46.
1,300 pounds I got.
Yeah, that's what the answer is here too. Okay.
All right.
Beauty. Thank you.
Look at this. Look at this mess that we just made up here, fellas. Look at that. I love it. I love this shit.
You got a buoyancy question or a example, or do you want me to find one? Or
Nah, I could fish one up here. Okay, let me do a buoyancy question with you, okay? A person weighs 150 pounds, has a volume of 2 cubic feet. Float or sink? So to give you an example, if I had a pool of water, okay, pool of water, there's my water, okay, full of water. And this is fresh water. I'm not talking about salt water, which is more dense and all that kind of stuff. And okay, I'm just going to use water, fresh water. And now if this person, so let me just not even talk about person. Let me just draw a little box here. So if this box, for example, was 1 foot by 1 foot by 1 foot, that would be 1 cubic foot, yes? Clearly. So if I take this box and I put it in the water, and that box sitting in here, oh my gosh, why does that do that? Okay, that 1 cubic foot box will have what's called a buoyant force pushing up on it. The buoyant force is directly related to the volume of the object. For example, 1 cubic foot box will have a buoyant force of 62.4 pounds. So there is 62.4 pounds of buoyant force pushing up on this box. So if I told you that this box weighs 100 pounds, how much does the box weigh when it's submersed in water?
38.6.
That's right. We take 100 and minus 62.4. So it's 38.6 pounds when it's in the water. This is the only way I can sweep my girlfriend off her feet. is by putting her in the swimming pool. 'Cause
I
I'm
love
just
that you
not-
had to look around before you said that.
So let's put it this way. This person weighs 150 pounds and has a volume of 2 cubic feet. Float or sink?
Float.
Let me draw it out. So in the swimming pool,
Oh, wait, no.
this person is in there. There is a buoyant force pushing up on this person according to their volume.
Yeah, they would sink.
So that's only 124.8 pounds of buoyant force.
Yeah.
This person weighs 150, so they're going to sink. But Mike, what if I put on a personal flotation device on this person? That personal flotation device has a volume of 1 cubic foot. Does the person float or sink?
Now he floats.
Because now we got 3 cubic feet times 62.4. So that's 187.2. So we have 187 pounds of buoyant force pushing up on that person, and that person is going to float now.
How would they, like, have you ever seen a worded question on an interprovincial where it would be a buoyancy related to plumbing or gas? Like, how would they, what would it normally be written as? Like, what are they talking about when they're asking buoyancy?
Some sump pumps use a float, don't they?
Oh, yeah.
So that's a principle of buoyancy to actuate a switch.
Perfect. Okay.
Okay. They may say something weighs this much in air. What does it weigh in water? The object has this volume. You know how long ago I wrote that IP?
Fair enough.
Connor was just born. Right, son?
You got it, Pops.
Just kidding. Just kidding. Okay, who's the dude that came up with using density, which is mass divided by volume is equal to density? Who came up with this formula to figure out if stuff will float or sink? Remember his name?
Archimedes.
Archimedes, yeah.
Archie. You bet.
That was for the crown, right?
That's
Gold
right.
crown.
So we figured out the density of a gold compared to the crown. And yeah, that is correct. Gave it a bath and figured out what its volume was according to its shape. Yeah, because he couldn't measure it. Couldn't tear it apart. Okay, what else you got?
I don't remember trenches.
Okay, that's a good one. They stopped doing trenches, by the way, but we can calculate one for you, okay?
So they've taken trenches off any exams?
It's not in our curriculum anymore.
But it's still fair game for the interprovincial.
It could be,
Okay.
okay? So let me come up with a trench question. Let's do this one right here. Okay, if you do get a trench question, I would suggest, again, if you need to write down some variables, please do so. If you need to write on the test, do so. Just erase it, put it in very light pencil and erase it afterwards, okay? But before we know trenches, we must, know OHS guidelines when it comes to trenches. Does anybody know how deep you can go straight cut trench?
5 feet.
I would have guessed a meter, but I can't remember.
Isn't it 1.8 meters?
I think it's
5.
It's actually 1.5 meters. Or
4.92. That's 5 feet, right?
it's not 5 feet. It's
Oh.
4.92 feet.
Okay.
Listen, for a guy that's not very tall, it makes a difference. It was, if I was 0.08 bigger, I probably wouldn't have to have a girlfriend.
You'd be 5 feet then, or what?
Yeah, that'd be huge. Okay. So that is the maximum allowed for a straight cut trench. Okay, always. Now look, this says 12 feet. This says 3. Okay, so this is in feet. So what's this measurement? I don't even have to look. What is this measurement?
4.92.
It always has to be 4.92 or 1.5 meters. It's never going to be deeper than that, bigger than that, or anything. Okay, so we have to always consider that first. Okay, excellent. So what I'm going to do is I am going to solve for this box first. Okay, right there. I'm going to solve for that. So if I put that down here, and this is what it looks like, right? This is just a straight rectangular box. I know how to calculate length times width times height. Do I not? It is equal to the volume of that rectangular box. So I just need my variables. So my depth, it says that the trench is 12 feet deep. So this is 12 feet deep. So this is 12, right? And it says 3.5 wide, 3.5 wide. And this is 115 feet long. So there we go. 115 times 12 times 3.5.
Don't you add the 4.92 to the 12?
No, because it's 12 feet deep. I need this measurement afterwards. This is 12 feet deep. Because I'm getting this box. You see where my red line is here? So that box right there is 12 feet deep, which makes this 12 feet deep. Did you see that? I don't want to move on till you got that. You got that?
Yep.
Okay. The 4.92 is going to come in handy in a second here. Okay, so I'm going to change colors just so we have a little bit of a difference here. Okay, I got that. So now look right here. You see this line right here? What is that measurement?
That's 12 minus 4.92.
That's right. So that's 12 minus 4.92, which is what? 6.08. No, 7.0. I can't even do math. 7.08. Yes? Does everybody concur with that? So look, I'm going to take this right here. I'm going to take this and I'm going to put it right here. I just want to put it over here. Okay? And that is like that. And now this side right here is the same. So I'm going to take that particular piece and I'm going to put it right here. And now I have another rectangle. And I know that this measurement is 4.92 and this is 115 feet long. I'm missing one variable. I am currently missing this measurement right here. This measurement I don't have yet. Trigonometry would say that if I take my run 4.92 and I multiply that by the tangent of a 30-degree angle, where did I get 30 from? This trench is 30. So 30/10 is 0.5774. It's a number that I memorized. I don't know why, but I do. So 4.92 times 0.5774 is 2.84. So this other measurement is 2.84. This is 2.84. Now I have a rectangular box length times width times height. 115 times 4.92 times 2.84. .84. So that is 1606, 1606.8. And I have to add this one to it. And I add, this one is 4803. So I add 4803 to that. Let me just move this up a little bit. Plus 1606. So my grand total volume is 6436.8 cubic feet. Now, if this triangle here, if this was a 45-degree cutback, the rise and the run are the same, yes? The rise and the run would be the same if it was a 45-degree cutback angle, right? And so then I would just go, this measurement 708, and this would have to be 708 as well. That was, okay. That's all.
Perfect, thanks.
Yeah. Whew. What else, fellas? Anybody? Girls, boys? I don't know who's in here.
You do this every Tuesday, hey?
Every Tuesday afternoon from 3 to 5. Same Zoom link. So if you already got the Zoom link, just keep it handy somewhere and just log in with the same Zoom link. Or you can always email me at doug.reed@sate.ca and I will give it to you if you need it. Okay.
Well, my brain hurts. Thank you very much for your help.
Sure, Spencer.
Have a
Hey,
good
take
night,
care.
man.
Hey, you know what? That beard, nasty looking, buddy.
Yeah. I'm the homeless guy that just showed up on site and started plumbing stuff.
Yeah, is it you living in a little trailer on the side of the job site or what?
Yeah, some days when my wife kicks me out.
Doing a little security on the side? Yeah.
Yeah, you can call it that. You have a good day, sir.
Take care, Spencer.
Yeah, Doug, I'll come up with some questions for next week.
That's a good idea, Mike. Bring me something that you want to know.
Yeah,
Okay?
we didn't know
Instead of
that.
me trying to reinvent the wheel here for you.
Yeah, for sure.
Okay.
Right on. Thanks, Doug.
Welcome.
Yeah, thanks, Doug.
Yeah, appreciate it, Doug.
Thanks, Doug.
Anytime. Again, I'm here for, try the wheel. I'm going to actually stop recording this.
Hey, Doug. Do you mind